Hello, so today we're going to finish up on electron configurations in regards to some special rules and concepts that we haven't really fully dived into in the last couple of videos, but I will divulge a little bit more today. So the first question I want to ask, is that in the previous videos I said that the electron configuration, is represented by 4 quantum numbers. Well, we haven't really dissected exactly how they're represented in the electron configuration. So let's dissect a little part of electron notation. If I take the electron configuration for helium, which is 1s2, I can say that the 1 is the principal quantum number, which represents the energy level of that particular orbital that those electrons are occupying. And then the s represents the orbital quantum number, which is the shape of that orbital, that sphere that the electrons are occupying. And then 2, that superscript, represents the number of electrons within that particular orbital. But you're probably asking yourself, where is the spin and magnetic quantum numbers? Well, those are actually demonstrated within the quantum mechanical model, which we've actually started writing a little bit in the previous videos, but you probably just haven't realized yet. So when you're writing the quantum mechanical model, you actually always label your orbitals with the correct correct part of the electron configuration that you're talking about. So 1s2, s orbital only has one orbital position, so we represent it with that one line. That orbital position is your magnetic quantum number. Okay, so this little line represents your magnetic quantum number. The spin number is represented by the electrons that are in that. So since there's 2 electrons occupying, they have to be of opposite spin. One's going to be a positive 1/2, and the other one's going to be a negative 1/2, because one's counterclockwise and the other one's counterclockwise. And the addition of those 2 create the spin quantum number, which in this case is 0. So the quantum mechanical model, which this actually demonstrates all 4 quantum numbers at the same time. So a couple of things you guys we've already talked about a little bit, but you're probably still asking yourself is, the D and F orbitals always start off at weird principal quantum numbers. Well, we're going to dive further into why that is. The reason why the D orbital wants to be a little bit lower is because the higher energy s orbitals are filled before the lower energy d orbitals, and it's because of the shape of the d orbitals. The s orbitals get filled first because they're more likely to react with atoms, and then after they get that, the d orbitals still need to be filled, so the electrons start going into the d orbitals, which just so happen to be at a lower energy level than the s orbitals before it. So when I'm writing out the electron configuration, let's say I'm looking at iron, we just follow the exact rules that we demonstrated in the previous video. We can say, okay, it starts off at 1s2 because we start off with off-bow principle. We start at the lowest energy level orbital, which is 1s, and we know we're going to pass helium, so it has to fill that 1s orbital, so it's going to be 1s2. If I read down to iron, I know that it's the 6th block within the 3d row, and so it's going to be 3d6 as its ending address. And then I read the rest in between, and I'll get 2s2, 2p6, 3s2, 3p6, and 4s2. If I take a little bit step further and I look at the ruthenium, which I believe is just a row below it, same thing. You start off at 1s2 because it's going to pass that helium as you're reading across the periodic table, and it's going to be at 4d6 because it's the 6th block within the 4d row on the periodic table. So as you're doing it, it will be 2s2, 2p6, 3s2, 3p6, and then the 4s2 will be filled first because that comes first on the periodic table. Then you'll fill the d's up, so it'll be 3d10, 4p6, 5s2, and 4d6. And again, you can count up the superscripts as the number of electrons. So, the atomic number of iron should be 2, 4, 10, 12, 18, 20, 26. So the atomic number should be 26, which means a neutral atom of carbon should have 26 electrons, and so on and so forth. So if we take a look at this, the F orbitals are actually not outside the main table. I've already kind of alluded this a little bit before. The way they do it is actually they are inserted right after the 6s and 7s blocks on the periodic table, but before the 5d and 6d orbitals. So the 4s sticks in between the 6s and the 5d, and then the 5f goes in between the 7s and the 6d orbitals. So based on the position of the orbitals, when you're reading that across the periodic table, when you're doing electronic configuration for those bottom rows, you have to include those F rows, even though it looks like they're not inside the periodic table itself. So if I take an example of tungsten, Okay, I know that I'm going to start off an off-balance principal and it's going to be at 1s2. Same thing, because it has to pass that helium. So its first orbital that's filled up is the 1s with 2 electrons. It ends on the 5d4 part of the periodic table, so 4 blocks in on the 5d row. But the thing is that as I read across the periodic table, I'm going to do my 2s's, my 2p's, my 3s's, my 3p's. I'll do my 4s's, jump down my 3d, jump back up my 4p, 5s, jump down my 4d, up to my 5p, and then I get to 6s. And we know that the 4f row is in between the 6s and the 5d. So it goes 6s2, and then goes 4f14, and then you jump into the d's, which is 5d4. Okay, and then we do the same thing for Hassium. So 1s2, okay, off-balance principle, 6d6 is where we're going to end up at. Follow the exact same thing, so you get up to the 5p6, 6s2, 4f14, jump into the 5ds, then you go to 6p6, then you go to your 7s2, and then you go into your 5f14s because the 5f block is in between 7s and 6d, and then you jump back into your 6ds, and then you get the 6th block in the d row, where you want to end up at. So as you may have noticed in the last couple of examples, some of these electron configurations can become really, really long. So, however, there is a little bit of a shorthand notation that we scientists use to demonstrate only the reactive electrons. So, before I go any further, when it comes to shorthand notation, you will only be allowed to use shorthand notation for any atom that has an atomic number of 37 or higher. So anything past krypton. Any krypton and before is fair game in regards to the entire electron configuration. If it's after krypton, you are more than welcome to use the shorthand notation that I'm about to demonstrate. Okay? Shorthand notation utilizes the elemental symbols of noble gases to shorten the entire electron configuration. The reason why is because noble gases are what are called inert or non-reactive. So we insert the symbol of noble gases that fills in the electron configuration for the noble gas, okay, which pretty much says that those electrons don't matter in regards to chemical reactivity, and then it follows with the reactive electrons after. So I'll kind of demonstrate what that means here in a little bit. The noble gases are the last column on the right-hand side of the periodic table. So this is where helium, neon, argon, krypton, xenon, and a couple other ones are going to be down there too. So we utilize these element symbols to insert into electron configuration to shorten it up a bit, so that way we're not writing tons of stuff out. So again, shorthand notation begins with the element symbol of the previous noble gas that came before it, and the rest of the electron configuration notation afterwards. So let's say I was doing tungsten again. We know that the electron configuration is this, okay? But if we look at the previous noble gas, if you're reading left to right, we know that the noble gas that comes before it is xenon, and we know the electron configuration for xenon goes up to the 5p6 mark. So the thing is that tungsten shares the same electron configuration up to the 5p6 mark, just like xenon does. So what we do is that we insert xenon into the notation for tungsten. We put xenon into brackets, and then we put the rest of the notation after. So what this is saying, okay, all of this right here is xenon, and then the reactive electrons after it are the 6s2, 4f14, and the 5d4, and that's where the shorthand notation comes from. Alright, so that's the end of this video. Again, another short video, but again, very important stuff. If you still don't get it, feel free to rewatch this video, pause it, take notes. Please come talk to me if you need to. We can break it down more step by step. I'm sure I'll be reviewing this a lot in class too. But feel free to email me, come talk to me. Otherwise, thanks for joining me on this video, and I hope to see you in the next one and in class. Bye.